Good morning, champs. Today we are going to solve a friction problem involving both a rough inclined surface and a rough pulley. Two masses are connected by a rope. One mass hangs vertically while the second mass rests on an incline. Our goal is to determine the complete range of values for the second mass for which the system can remain at rest. The hanging mass is 80 kilograms. The incline angle is 25 degrees, and the coefficient of static friction is 0.25. Because the pulley is rough, the tensions on the two sides of the rope are not necessarily equal. We call the tension on the hanging side T1 and the tension on the inclined side T2. At impending motion, the ratio of the high tension to the low tension is given by the Capstan relation. But before using that equation, we need the contact angle of the rope around the pulley. This contact angle can be confusing, so let us first look carefully at the geometry. The left-hand rope segment hangs vertically. The right-hand rope segment is parallel to the inclined surface. That detail is very important. Because the rope is parallel to the incline, changing the incline angle also changes the direction of the rope. Now imagine the special case where the incline angle is 0. Since the rope is parallel to the incline, the right-hand rope would then be horizontal. The left rope would still be vertical. A vertical rope on one side and a horizontal rope on the other means that the rope contacts 1/4 of the pulley. 1/4 of a full circle is 90 degrees. So for this geometry, when alpha is 0, the contact angle is 90 degrees. Now return to our actual incline angle of 25 degrees. The right-hand rope is tilted downward by 25 degrees relative to the horizontal baseline. Because the rope stays in contact with the pulley for that additional angle, the contact angle increases from 90 degrees to 115 degrees. So for this particular setup, the contact angle is 90 degrees plus alpha. This is not a universal pulley formula. It works here because the right-hand rope is parallel to the incline and the left-hand rope is vertical. If the rope on the right were not parallel to the incline, then the incline angle alone would not determine the contact angle. This is why it is safer to think in terms of the actual rope directions rather than memorizing 90 degrees plus alpha. We now convert the contact angle to radians. 115 degrees is approximately 2.007 radians. Using this value in the Capstan relation, with a friction coefficient of 0.25, gives a pulley friction factor of approximately 1.652. This means that at the friction limit, the higher rope tension is 1.652 times the lower rope tension. Now consider the hanging mass. Since it is at rest, the tension T1 equals its weight. This gives 784.8 newtons. We now analyze two limiting cases. First, suppose the second mass is too light. The hanging mass tends to move downward and pulls the second mass up the incline. Friction on the second mass therefore acts down the incline. In this case, T1 is the high tension. Dividing T1 by the pulley friction factor gives T2 equal to approximately 475.2 newtons. Now isolate the block on the incline. Its normal force equals the normal component of its weight. At the limiting condition, static friction equals the coefficient of static friction multiplied by the normal force. Along the incline, the rope tension acts uphill, while gravity and friction act downhill. Applying equilibrium gives a lower limiting mass of approximately 74.6 kilograms. Now consider the opposite situation. Suppose the second mass becomes too heavy. It tends to slide down the incline and pulls the hanging mass upward. Friction on the second mass now reverses and acts uphill. The high tension side of the pulley also changes. This time, T2 is the high tension. Multiplying T1 by the pulley friction factor gives approximately 1,296.2 newtons. Applying equilibrium to the second mass again, with both tension and friction acting uphill, gives an upper limiting mass of approximately 674 kilograms. Therefore, the system can remain at rest when the second mass lies between approximately 74.6 kilograms and 674 kilograms. The key lesson from this problem is that the pulley contact angle must come from the actual rope geometry. In our setup, the relation 90 degrees plus alpha works only because the right-hand rope is parallel to the incline, and the left-hand rope is vertical. After the contact angle is known, the rest of the problem is handled by considering the two possible impending motions separately. When the motion reverses, friction on the block reverses, and the high and low tension sides of the rough pulley switch as well.